So definition, I need to define a covering before we define compact.
Oh,
But it sounds like a cub to cover something, like it's pretty actually intuitive.
okay.
So
Oh, hey, okay.
a connection. Oh, so
You gotta wait.
here's how this is gonna work. There's a really, really tough theorem but it's really central to stuff.
That will comes next, yeah.
Well, no, it's more like there's simply ordered sets with the least upper bound property having their closed intervals being compact, because then you can take all of the closed intervals of R and say, it's compact, and you don't have to do anything about it. So
That's cool.
it's an early result, but it's really hard. I don't know why it's so hard to prove. So I haven't completely actually wrapped my mind around the back half of the proof.
Okay.
So the first half of it, I've got pretty locked down, in terms of both the intuition for it and then how it works. But then I'm gonna just use some time to try to figure it out. But yeah, first definition. Did I ever start recording? I did. Okay. A collection. Script a notational thing, Victor, is if it's in script font, it's denoting like a collection where the elements of the collection are themselves sets. Or if it's just a capital letter, then it's just like a set.
So a collection is a set of sets?
Yep.
Okay.
So collection script A of subsets of a space X is said to cover the space X, or to be a covering of X if the union of the elements of the collection is equal to the space. It is just called an open covering of X if its elements are open subsets.
Wait, so to be clear, do the union have to equal A, or can it be something, or have to equal X, or can it be larger than X?
It just equals the set. Yeah. Now, if we're talking about later, we'll have subsets of subspaces, so you can technically let it be bigger than, but for like just the cover is you're just covering all the elements that you got.
Okay.
All right. So then we define compactness from here. So a space X is said to be compact. A little less visually intuitive than connectedness. If every open covering script A of X contains a finite subcollection that also covers X.
We call that a subcovering. My class that I took
Oh, so you're
when
saying,
I was your age.
so you're
Well, they were
saying
older,
that
actually.
A can't be reducible. There's always gonna have something in A that's redundant.
Yeah, so the idea is X is a space, which means that there's been a topology applied to it. And so that means that the elements of that topology, those subsets, would now, because this is an open covering. So we have a bunch of different elements of the topology applied to X that form the elements of this collection. So we're collecting a bunch of these. that could be an infinite number of subsets. But we're saying it's to satisfy compactness. We don't need all infinite number. We can find just a finite number of those open sets, and that'll still have the same result of covering the thing. Because if you think about it, like if you're covering a surface or covering your bed, and you throw a bunch of blankets on it, there might be overlap. So you might not need every single one to technically cover the all of the space on your bed or whatever. So there, that's basically all it's saying. Is that it'll be compact if you don't need an infinite number. Um, basically all of the open sets of the topology to cover it. Okay, so the immediate issue, which motivates kind of what we're proving today, is that the real line is not compact. Because we can't just take finite subcollection of from the elements in the order topology here. And then that's not going to take care of all of the real numbers. So we don't have a finite subcollection, so it's not going to be compact. It's connected, it's not compact. And then actually there is a fun way that we can do. Well, no, because I want time to finish this theorem. It's so hard. And it shouldn't be as difficult as it is, but it's so difficult to understand for me. Here's what we're trying to prove then. Okay, so if R is not compact, then why do we care about, what we care about for compactness is going to be the subspaces of R. So if R is not going to be compact, we're interested in the subspaces of R, which is going to be closed intervals of R. So the theorem, we're not going to prove it just for R, we'll prove it for basically any simply ordered set with least upper bound, right? So let X be a simply ordered set having the least upper bound property. So in the order topology, each closed integral in X is compact. So we'll do the proof, but basically what we're talking about here is eventually we'll apply this to a corollary that basically R is like X here. R is simply ordered and has the least upper bound property. So that'll be good to know because then we can say that all the closed intervals in R are compact. So we'll be able to take, well, let me first go. If I have A is less than B in R, then this closed interval AB is compact. Okay.
So, just to verify, simply ordered basically means that it makes sense to have a less than or greater than in this set, right?
Yeah. You just assign the order relation less than, and then under the order, with R, it's just,
Okay.
yeah.
And
We're
then-
not doing a product, so we don't need dictionary order or anything weird.
Okay.
Yeah.
But, so what's the least upper bound property again?
Yeah, least upper bound property is saying if I take some set and then I take some subset of S, then for all subsets A that are bounded above, then that each of those subsets was going to have a least upper bound, and that needs to be true for all of the subsets of a set.
Okay. I get it.
Yeah.
Ish.
It's a lot of little ridiculous details, but okay. Let's break the proof down into 4 separate steps. So we need to start with some stuff. So given A less than B, I'm gonna let script A be a covering of the closed interval AB by sets open in AB. So we're just setting up definitionally an open covering of AB and the subspace topology. Subspace topology. And we use the subspace topology because last semester we proved that they're the same as the order topology. So this is same as the order topology. Okay. So what we want to show overall is basically that there exists a finite subcollection of script A because it's this open covering of the interval that covers covering closed interval. And if that ends up being true, that's the whole point of the theorem. So we're saying that it's compact. Okay. So we first show that if I take some point x that is in this closed interval AB, such that x is not the top of the interval, so it's not B, then we're guaranteed the existence of some y that is in the interval where y is greater than x, such that the closed interval, if we take just from x to y, that can be covered by at most two elements of A. And that's good because, I mean, only two, at most two is going to cap it, so it can't be infinite. So there's going to be two ways to think about this. If we have immediate successor, then it's essentially going to be endpoints of the elements of the covering. And then if it's not, then we can just contain it inside of one element of script A. So let's do the immediate successor first. If X has an immediate successor in X, which in R, that would be the case. We have immediate successors. Then we're going to want to choose Y. So choose Y to be this immediate successor.
Hey, Scott.
Yeah.
Real quick, is this only valid for infinite sets?
Well, so we consider infinite sets because if the set itself is finite and then we apply a topology to it, then technically if we do any such open covering because the topology in itself is finite, it's definitionally going to be a
Oh.
finite collection. So the subcollection can just be the topology itself. And then you've now covered it with open sets and there's a finite number of those, so it'll be definitionally compact. So yeah, I mean, this is allowing us to take a look at subspaces of infinite sets. So then we can see whether or not these intervals of infinite sets can be compact instead of just finite stuff. But yeah, does that make sense?
I think so, yeah.
Okay. So X has an immediate successor, but we want Y to be the immediate successor in X. So, oh, actually, there's a nice little diagram that I think I probably can illustrate this if I really think about it. So the interval xy then is just 2 points. That's what it means. Consists of the 2 points x and y. So that it can be covered by at most 2 elements. Okay, so where's that restriction coming from? If I have my simply ordered set X, and I choose A less than B, and then I select an X in the interval. The first case is immediate successor, so I'll just kind of illustrate that right there. Immediate successor.
I thought you couldn't have that with infinite sets.
What do you mean?
Well, I thought that.
Well, under the order relation, then now this is just has to do with the property what X is, but the kinds of elements. In this case, this isn't always going to happen. So there's not necessarily always an immediate successor. So after this, we'll do a case where if X does not have an immediate successor, there's still a way to get it to work. Here's the case where at most two, because now I can't have single point subsets. But those single points, because those are the only two in this particular subset, because I have a covering of open sets, then I can take this union and essentially those 2 points, which then form those endpoints, can be covered or included. So then this is going, I'll just call this, say, like G and H, where these points are. Because then if I want to express the XY, then I found a way to essentially contain them with open sets. So it's a subset of
So why the boundaries not be contained?
G to X and then Y to H.
I thought the boundaries weren't contained in an open set.
Sorry, yes, this is supposed to be closed.
Oh, okay.
I So we include X, we include Y.
Gotcha, and H.
Yeah, because we don't need to, because these would be,
Oh, I see what.
Yeah.
Yeah.
so we'd have, this doesn't necessarily have to end in here though.
No, I think it would be every point has to be within some element of the covering. And so pick an element where X is in there, then either Y is in there and then you have one, and if Y isn't in there, then that's when you need two.
Okay.
Because Y has to be in one as well.
Oh yeah, that's what I was thinking, because it seemed a little overcomplicated. So on the at most two thing, I think
Yeah.
I think they're just saying that since they're distinct points, whereas one is the immediate successor, then you can't. And then if X does not have an immediate successor in X, then we choose Y a little bit differently. So we're going to choose an element. We'll just call it A. That is in this collection. Such that X is in that particular element. So this is what you're talking about, just
Right.
choosing an element for it. And then we initially made sure that X was not equal to B. And also A is open by hypothesis. So then we have some XC as a subset of A for some C that's in interval, which allows us to choose a point
There's a long stage bit, and then what's the that?
Y in
Touch that.
What's that?
X to C. And once we choose something in the open interval, but this is closed, then that means XY is covered by the single element A. So I think if I understand this reasoning correctly, here's our space. And now we don't have an immediate successor. I choose an X in the interval, I choose a y that's greater than x. This particular interval is xy, and I want to say that you're actually able to just basically choose one of the open sets that's inside of here that essentially will contain everything. Now, yeah, because if I'm putting y essentially in the open set, so y is in open here, and a is like all the way out. Since I'm not choosing y to be equal to x because y is not an immediate successor, then we can always choose one element for it to be in. So, cool. Okay, and then it starts getting a little confusing.
Oh, so why can't that work for an infinite, for like no, it wouldn't just be infinite, but like the real numbers?
Well, I mean, we will apply this to the reals, right? When the theorem is applied to the reals.
Because I thought the theorem's only for a subset, or subspace or something like that.
Right, so closed intervals of R.
Yeah. But why doesn't it work for all the real numbers?
Well, for all of the R, because the order topology has an infinite number. Like in order to cover all of R, there isn't just a finite number of open sets that'll include every single real number.
Do the open sets have to be finite?
Yes.
Yeah.
You're not allowed to choose infinity as like the endpoint.
Okay.
Because then you could just come up with one.
And then the entire study of topology would become kind of useless.
You're not allowed to use infinity as one of the endpoints.
Now you can have rays and you can have subspaces of your topology, but that itself can't be an open set. Yeah. So now we're going to let the capital C, so this is be the set of all points where y is greater than a of this particular closed interval, such that we want this smaller interval that goes from a to y, that can be covered by finitely many elements of A. So we're basically choosing to define a set as points y that are going to essentially satisfy compactness. So we want to have points that y that are greater than a that are not that, so that this would be compact. And I think if I understand the strategy correctly, if we show this step, then the ultimate goal is to essentially push this all the way up to the end. So then it wouldn't just be true for stuff that's less than b, but you can make that true all the way up to equal to b. And then at that point, you've just shown the entire interval itself is compact. So I think that is the strategy. And I'm going to now try to rationalize this reasoning in my head.
I thought you already did this. Wait. So before you didn't already prove that the finite set what finite the subset was compact?
Not quite. So what we showed was if I happen to choose a point in the interval, then there exists some sort of an element that's past that chosen element that lets me essentially cover that with at most two. So essentially we're guaranteeing there's a finite way to accommodate that selection. And now we're gonna apply that
But I thought that
result.
choice of x was arbitrary.
Yes, but it wasn't A. So X was not the endpoint A. So we were making X greater than A and sticking it somewhere inside of the interval. And it didn't necessarily, because now we're having to back it up to the entire interval AB. So we're taking like even the subset of a subspace of the entire thing.
Okay.
Because now I can apply step one, because I'm basically saying that I've chosen an element that's greater some element, and then we know that that's going to be able to be covered by at most two things, which is finite. So if I apply step one, oh yeah, so where there's different cases to the case where I choose A to be the bottom point now, so that's what we're talking about. And then we see that there's going to be at least one such y. And we have that just so that we can guarantee that C is not empty. And now we're defining a little element C to be the least upper bound of that set. Yeah. And that's going to tell us that A is less than C is less than or equal to B, and then now C is the thing we're pushing up to B. So if I take, okay, so here's that scenario. Here we have X, and if this is A, and this is B. So we're looking at, right now, we're looking at the whole interval, and I'm selecting points Y, so Y's that are greater than A. So like Y's that are greater than A, like y1, y2, y3, such that this closed interval, if I go from here to here, or from there to there, from there to there, that these can be covered by finitely many elements of A. And eventually the goal is obviously just make that true all the way down. And if X is equal to A, so the bottom is here, and then I'm going to have these intervals from X, Y, 1, so that's where we're applying step 1, where it's X and Y, you can choose, you can cover what I mean, those two. This is not empty because step 1 is guaranteeing that existence of at least 1. And then because we have at least 1, we can choose a bound. So essentially, if this is going to be the furthest extent we can push this out, so that it's still true that we have a compact interval that's contained inside of AB. Which is why we're not letting C be equal to A, because we've already chosen bottom of that to be X. And so there'd be no point to have a single point interval.
We're going to show that C is equal.
Yeah, so that this least upper bound that's A.
I do have a question though, because before you had your two methods from step one. The first method where it had an immediate successor involved having two subsets, right? Like it's in that, right? But then here,
102.
1 or 2, yeah.
oh, okay.
At most 2. So if one fails, then you only require one more to get the last one.
Well, it's so in this case, if x equals a, then you can't use that first set. So what you have to do?
Well, I mean, so the thing is, in one sense, we kind of are actually just repeating the reasoning. That's why we're citing the step, is because, yeah, that we're basically showing that it worked somewhere in the middle. So now, if in the special case where I set X equal to A, well, it doesn't change anything. The result is still, we can still apply it to some of these.
Can just set y equals b.
Can't set it.
Yeah, you can't set that. So we have to claim that it's greater than what we're starting at, because then that's going to give us a closed interval. But these guys, so imagine, so in this set C is going to contain all of these Y, like Y1, Y2, Y3, etc., right? And somewhere in there, there's going to be the least upper bound on all of these, which is what we're calling C. So C is somewhere in here.
Wouldn't that be the biggest upper bound?
Yeah, well, I mean, like you're no see, that's the thing with these kinds of theorems, is it's kind of like the obvious results. So you look at it and you're like, because. So yes, I mean that is the it's visually obvious. It's like, why don't you just choose that, essentially? But that's the goal, is we want this to be in that set.
I see.
Yeah. Step 3, it will help us connect some of this stuff. I am thinking about the way that we do this contradiction, but it might help if I draw a picture. Okay, so we're getting there. So we observe that C has to be in C, the way that we define it. So that is, if I take A up to C, this can be covered by finitely many elements. It's compact. Finitely any element of A. So we're gonna choose an element of the collection. So we're gonna choose the specific one that contains the C. And again, recite that A is open because that's hypothesis. A is open, and then that means we're going to have a subset of the form D to C as a subset of A for some D in AB. And now if C, so what we're gonna do is we're gonna do a contradiction because we want C to be at C. So we're gonna assume that C is not if we assume that C is not in C, then that would mean that there has to be that a point Z that's in this set satisfying that Z is found in this open set D to C. That would lies within A. Because otherwise, D would be a smaller upper bound. Smaller upper bound on C than C itself, which we define to be the least upper bound. And then we have if, well, since Z is we're putting this in C, then if I go from the bottom of the interval up to this other lower point Z, that can be covered by finitely many. And since it can be covered by finitely many, let's just choose a finite number of subsets n elements of script A. So now, if I start at Z and go up to C, then this still lies in the single element that we chose containing, let's say. So then I can express from A to C as the union starting at A to Z, and then from Z to C. However, this can be covered by not n, but now it's being covered by n plus 1 elements of A, which then would put C back in C, which is contrary to what we assumed.
Scott,
Yeah.
there's something I don't get because you already shown that C belongs to C, capital C. So then you're using if then statement. It looks like you're trying. I'm not sure if I'm misunderstanding, but it looks like you're trying to do the contrapositive
So you're
of
talking
this
about
thing.
his first statement?
Yeah, so because what I'm
Really?
thinking way back in I learned in discrete math, if P then Q, and then we know already that the P is false, but that means that we can't know anything of Q. Is that right?
Well, so his WST means he wants to show that C is in C.
Well, is that by definition? Because C it contains all the sets of the upper bound.
Sets don't always, a set is not required to contain its least upper bounded.
Wow, what?
Yeah, sets aren't required to contain their or subsets aren't required to contain their least upper bound. Well, think about, so for example, think in R, and it's where we can kind of start, we motivate notions of limits, because if I had some open interval 0 to 1,
Okay.
well, what's in upper, we could have some sort of a set of upper bounds for this interval. So like the number 2 would be an upper bound because it's upper here, or the number 4 would be an upper bound. But we beg the question, okay, how close down can we get? What's going to be the smallest element of this set, which is upbounding 0 to 1. And then so I could get closer and closer. And the idea is eventually we find that, well, you can't get any smaller than 1. But 1 now is not included in this set. However, it is an upper bound. And there's no way for me to get less than that for it to still satisfy the property of being an upper bound. So this subset, though, does not include 1. So 1 is not contained in 0 to 1. However, 1 is satisfying the property of being the least upper bound of this integral. So we have this, so think of C as like an open interval, right?
Okay.
We want to guarantee that no, in fact, this isn't going to be some open thing. It will actually be closed, where we do contain the C, which is acting as 1 in this case. We want that to be true. So what we're doing is we'll just assume that it's not, and then it'll lead to a contradiction where we're saying that I can cover it with n elements, but covering it with n means I'm covering it with n plus 1. And then because there's a logical contradiction, our hypothesis that this C was not actually included in the set means it must actually be part of this set.
I see.
So that's why we have to do all this rigmarole, because we can't just take for granted, we can't always take for granted that least upper bounds are necessary. They're not necessarily in here set, yeah. But yeah. gotta patch all the holes. So it always works. Okay. That's starting to make more sense than the first 4 times I read this. So the roadmap so far is we have, okay, I can choose an element in the interval, and regardless of whether or not it's an immediate successor or not, at most, I can cover it with 2 elements, which basically, for all intents and purposes, means it'll be compact because that's a finite number of things. Then we say, okay, then in that case, we can reframe the problem to just simply showing that if we take the set of all the possible things that are greater than the starting point, which is the endpoint, we can just push that all the way up to the end of the interval. And then saying, okay, and then if I want there to be a least upper bound, that can be in fact in this set. So then now the last thing we're going to do is we're just going to do the last step, which is saying that that C corresponds to B. And then we'll have covered all of the cases. So finally, we show that, or I want to show, that C is B. So we're going to do this by contradiction. We're just going to say, well, if I want it to be with B, let's say it's not. Let's say C is less than B. And so we can apply step 1 to the case where X, we choose C as X. So we're saying, okay, well, if it's not allowed to be here, then now C has to be contained somewhere inside of here. So if I've got A and I've got B, we want to show, like, the proof is true basically that C is equal to B. So we'll say that C is not. And that means C is going to be somewhere in here. C is less than B. But as you pointed out, we already showed in the very first thing we did in this proof, that means there's going to exist some selection of Y. So is the Y there, or is the Y there? But either way, we'll run into a contradiction because this isn't possible. We have to have C correspond to B. So we conclude that there exists Y.
Oh, is that why you need to prove that C is inside the big C? So
Yeah.
that you can do that?
Because if not, then we don't necessarily actually have C in this set of possibilities and choices of Y that are greater than A. We can choose a Y in a E where Y is greater than our choice C. So C to Y is compact, so it can't be covered by finite many elements of A. And then we showed in step 3 So we just showed that the least upper bound is actually indeed in this set C. So that means AC is compact, can be covered by finitely many elements. Okay. So I can write this interval as the union from A to, oops, sorry, no, not AC, I'm going to Y first.
Thanks for the topology of this.
Script A,
Yeah,
that's the collection of open sets in the covering.
every other set. Sure.
Not necessarily. It's a covering.
Oh, okay.
Can also
There may be many different coverings.
be covered.
So compact means that no matter what covering you choose, you can always find a finite subset of that covering that will still cover it.
Good.
So this means that Y is in C, which would contradict the fact that Y, or that C, is an upper bound. Right, so then if C is not allowed to be B, then we're given the existence of Y. Guess what C is supposed to be satisfying the property of? Well, it's supposed to be the greatest, it's supposed to be the least upper bound of this lower interval. Issue is now we've given essentially this element, which would cause this to not be an upper bound. That can't be true because we just showed that that has to be in that set of options. So it's all the way, it has to correspond with B. Whereas in C being equal to B is the only way you don't run into a contradiction. Okie dokie. Okay, corollary. So we did all this. So now we can say,
That's not one of the proofs from the book, right? That's not the most beautiful proof ever. It works, but
this is the, I borrowed Munkres structure. There's probably a better way to do it,
well,
but I don't know.
I don't know. So
Some of them are just tedious.
yeah, maybe it's just one of those.
So the fun part is after all this, we can say, well, good. So every closed interval in R is compact. Ah. Finally, yeah. So it gets pretty particular, but yeah. So closed intervals are the little superstars of, at least closed intervals in R, more simply ordered sets, because they're connected, compact. Their finite products are connected and compact. Their images are connected and compact. Actually, when I was asking you about in when I was in analysis, I couldn't understand why we had what was motivating the difference between just continuity versus uniform continuity. And it has to actually do with topological properties. Continuity is just for only we really have just connected, and so images of connected things being connected in the domain versus compactness, which is a stronger property. So then compactness is going to actually I'll show I went through that proof.
So everything that's compact connected.
Ooh, I don't think so. No. No. No, because you could have
To disjoint.
disjoint things, but still accounting for everything. Yeah.
Yeah.
So it doesn't require connectedness.
Interesting.
Um, so compact subspaces of R being both connected and compact is makes them very strong topologically. Because actually, it's not just regular connected; they got path connectedness too. So it's path connected and
No, very nice. Let's try and see what that word is called.
What?
There must be a name for it.
which one?
For a space that is
Both compact and simply connected. Yeah. It'll probably just say something like, the real life. uh,
or the compact connected space. It doesn't have a special name. I thought it would.
that's pretty special. Mathematicians really pulling a leg. They're giving it a dash, an end dash between there.
Usually somebody's name is what I'm looking for.
Well, so Bolzano, there was a little bit of history on that. I think as the Bolzano-Weierstrass was a weaker form essentially of compactness, but it was more limit point compact. So Munkres separates out limit point compactness with compact. And
Interesting.
he had reasons for why it used to be held that way, and it's because the people who were doing it for analytical purposes. But then he's like, well, analysis isn't the only thing you can do in mathematics, and oh no, there's more. Yeah. But this is so we're stepping down in abstraction to calculus, which is a little bit more relaxed. Let f take x, y be continuous map, so be a continuous map of the compact metric space. And now the word salad just gets longer the more words we learn. Compact metric space. And a metric space in simple terms is basically you got a topological space. Well, you don't actually have it, but you can have a space that you can define in metric, which is just measure. So like distances have mean something. And we'll take that, we call that a set x. And the way we define how distance is defined is some dx to the metric space. So we don't require the domain space to be compact. It just needs to be a metric space.
Wait, what's a metric space?
Basically take a set and apply a metric to it. The metric is going to be, so the metric here, I'll give you an example and it should suffice. The metric for R is dxy is the distance between those points.
Oh, okay.
So when you think of metric, think distance, but generalized outside of what we think of in like numbers or like the real world. So you don't necessarily need to have a metric on just reals. What if you just define a random set? What does it mean for them to be distance between points in that set? So technically this is kind of out there and not restricted to R, but we will apply it as example to calculus. Then f is uniformly continuous. The tougher the hardware, the shorter the theorems. So being able to, this is just a really, really big property to put on that. So if you can guarantee compactness, then so long as you go from a metric space into a metric space, that domain space being compact is going to guarantee your continuity, uniform continuity. So
What's uniform continuity?
what I'll do is I'll show this, and then the example that you can apply it to, it'll look familiar when you see the epsilons.
Okay.
So given any positive epsilon, we're going to take the open covering, of y balls for a point y with a radius of half of epsilon that was chosen.
That's just like looking in.
Radius epsilon. Yes, the convenient choice. Nah.
Magic.
Or a really, really good guess. But A, B. the open covering of X. Open covering of X.
Wait, should you say the open covering or an open covering?
Oh, well, I'm gonna specifically, so this specific cover, I'm gonna take all of these Y balls and then take their inverse images back into the domain space. So it's a very specific open covering. The open covering of XY, the inverse images. Inverse images of these balls under F.
That sounds like a radius.
Yeah.
Well, actually, epsilon acts as a so regular continuity, epsilon is a radius. Uniform continuity, epsilon is a diameter. So it's interesting. Although I'm sure there's a way you can rewrite the simple ground, but choose. So, oh, I forgot to define what a Lebesgue measure is. Whoops, it doesn't matter. I'll just believe me. So choose delta to be a Lebesgue number. Yeah. Big number for the covering. Okay, a Lebesgue numbering for the Lebesgue number of a cover is essentially if you take an open covering of a metric space, so you have a metric space, given an open covering, and then if you take some subset A, where essentially the diameter is contained less than delta, then if X is then compact, and there exists some number delta that's positive, so that'll be true for all of your subsets A, then we'll say that that chosen number delta is the Lebesgue number for that. Yeah. So that's all. That's what this is saying. It's basically just a way to get around having to repeat. Make sure your diameter is under. Um, so then, if I choose 2 points x1 and x2, say, in my metric space X, such that their distance is less than this Lebesgue number, the 2-point set x1 and x2 has diameter less than delta by choice, so that its image f of x1 and f of x2 lie in some ball. Basically, there is guaranteed to exist a ball, y ball, by epsilon halves. Then, because it's a that ball, distance in y between these 2 points, f of x1 and f of x2, will be contained in epsilon by choice above for the balls as desired. So they didn't have a picture of this in the book, so I kind of came up with a little labeling system for this.
Version.
Yeah.
Book have any pictures?
So now this can be applied down.
So he ended basically with the definition of uniform continuity. So that shows that it's uniformly continuous.
Yeah.
So the difference between x's has to have a difference in y's.
So
It's uniform.
example. Calculus.
So is it just uniform with metric space? No, sorry, is it just continuous with metric space?
No. So you can have continuous functions that go to infinity, like
Right.
like y equals x squared goes to infinity,
Yeah.
but it's not uniformly continuous because the distance between y's for a fixed distance will grow and grow and grow.
which is why we don't talk of uniform continuity as being R to R, because R is not compact. But we did just prove for like half an hour that this will be compact. So here's what we're talking about, FAB to R, and we have something that is compact metric and metric, and we're going to define what these distances are. So I want the metrics dx and dy to correspond with simply being that dx, the distance between any 2 points, is that real line distance. That'll be x, y, and r. So here's an example. So if here's A, and I'll do B here. So let's say this starts somewhere and have it end somewhere. And then now what I'm going to do is the uniform continuity is just a choice of positive epsilon somewhere in the domain metric space. So if I choose any epsilon, so the idea is I'm going to draw a pretty big epsilon, but then it doesn't matter what size it is, so it could be really small. That this is my epsilon. And then if I take, let's see, that is my, and this is going to be, the part of this is there exists this choice of a big number delta.
Right, you do that all over the place, and then the biggest
So
one,
it's like-
your biggest one is basically your delta.
Or now that I've defined these two, so the thing is, it's the epsilon informs the delta, and regardless of what I choose for this, now, because the way that it works is in applied to calculus, actually I don't like the word given because you can just use for all. But if I choose a positive epsilon, that delta that's positive. So now the additional condition is I'm going to take some x1 and x2, right, that are inside of this particular interval, so that in the event that I actually choose it so that their distance inside of the metric space for x, if that distance is contained inside of that resulting delta, then the distance in the other metric space between them. So this visually kind of represents that. So then that's why I can't choose I can't choose x values that are outside, because then it's not guaranteed. It wouldn't be required to. But if I do select them in such a way, and this was stronger than regular continuity because you had a point x naught, and then you chose the minimum of delta from as a radius, whereas now the delta is just this this set fixed interval, so that so long as it doesn't even matter. So I could have had the x2 be the end point, but that distance will guarantee that no matter what those selections are, then
Oh, you have to do the larger. Yeah, it's pretty nice. I like that.
this would be
Okay, I have to get to my next team.
yes.
So that's good. That's a good way.
I think though, I thought that wouldn't work even if you got just part, well, like just the lower part. Like let's say you don't go to infinity. But then the largest delta will be right at the base, right? Because you'll have that.
Well, the delta isn't being informed by the points, and that's the difference.
Let's do inform of
Delta is only
epsilon.
informed by epsilon, and then if you satisfy the necessary condition for the distance, that metric being contained is it's a conversation about the metrics in the domain interface. Okay. I'll see you next week.
Okay, maybe.
All right.
Good luck, Wayne.
Yeah.
Should probably put these back. Ah,